All right, so Pythagorean theorem identities are, as the name suggests, connected very closely to the Pythagorean theorem. When we talk about the Pythagorean theorem in a geometry class, we usually are talking about something like a squared plus b squared equals c squared, and how that relates to a triangle is in a right triangle where the legs are a and b and the hypotenuse is c. So that's our Pythagorean theorem connection. The Pythagorean theorem-like statement that I'm going to work off of is the one that looks like this. And that is, if we kind of come back to a triangle that we could put on the unit circle, I could create that same relationship, but instead of using an a, b, and a c, I can use an x and a y and an r. So x squared plus y squared equals r squared is kind of the trig world version of the Pythagorean theorem. Okay. Because when we talk about a triangle and we talk about sort of it relating to locations on a unit circle or an angle of rotation, theta, we talk about x and y and r. Unit circle, we know r is 1. And the other thing we learned, kind of from this triangle, is that when I talk about the sine of theta, if I look over here at my triangle, in the spirit of SOHCAHTOA, sine is opposite over hypotenuse, which means y over r. And we can talk about cosine as x over r. We did that. We talked about that in Unit 1. We connected the SOHCAHTOA relationships in the right triangle to an XYR thing where XY represented an ordered pair on the unit circle, because you could still also think of XY as the sides of the triangle. Okay. All right, so this is all the buildup to how we're going to create these Pythagorean identities. In reality, if you know one of them, if you learn one of them, then you'll be able to figure out the other ones directly from it. Okay? If I take this relationship and I divide everybody by r squared, which is legal to do. If you have a relationship, an equation that's true, and we want to look at it a little differently, we can do something to it as long as we do something mathematically legal and we do it to both sides. So let's say I take everybody on both sides divided by r squared and then rewrite the results. R squared over r squared, well, anything over itself gives you what? 1. So that part's easy. And if I want to trig this a little bit, an x squared over an r squared, okay, I'll go on another page, an x squared over an r squared is like having an x over an r and having the whole thing squared. And we just decided or agreed or talked about the fact that x over r in trig world is a cosine. So we're going to replace x squared over r squared with cosine squared. Now, one of the weird things that we do with trig functions, just a weird notation thing, is when we want to square a trig function, a lot of times the way that it's written is going to look like that. So that they put the 2 here. So it's the cosine that's getting squared, the cosine of the theta all squared. If you put the 2 out here, kind of floating around at the end, then that might make you think the thing that's getting squared is the angle. It's the cosine of the angle. We write it like this, but it means this. And if I follow a same sort of plan of attack, when I looked at the y squared over r squared part, that's the same as that, which is a sine squared. And I'm going to use my sort of wacky trig squaring notation. So the bottom line is, when we look at all these different combinations of x's and y's and r's, and we kind of move things around and rewrite them and re-represent them in a different way, the x squared plus y squared equals r squared relationship can be transformed into the cosine squared of an angle plus the sine squared of the same angle is always going to equal 1. Now, if I could put like flashing lights and fireworks and big whatever around that, I would, because that's how important that identity is. A lot of people don't remember much from high school math, for sure, because they don't use much of it. But just like a lot of people, if you went up to them and you went a squared plus b squared, they'd say equals c squared. If they took a trig class, they may not remember very much about trig, but a lot of people, times you remember this identity. Cosine squared plus sine squared is equal to 1. That is our number one top identity that we're going to memorize. It only works for squares. It doesn't work for like cosine cubed and sine cubed. It doesn't work for cosine and sine all by themselves. It doesn't work for square roots. It's a special identity. It just works for a cosine squared and a sine squared. We can check that for lots of different angles and find out that that actually does happen. You know, like if I'm talking about pi over 6, you don't have to necessarily write this down. You can just kind of watch what I'm going to say. So cosine of pi over 6 is root 3 over 2. And sine of pi over 6 is a half. The identity says what should happen is that this should be true. That the cosine of pi over 6 squared and the sine of pi over 6 squared added together should equal 1. And you can check that over and over again with different angles, and it'll work. Square root of 3 over 2 squared is 3 over 4. 1/2 squared is 1 over 4. 4 over 4 is 1. Any angle you put in there, as long as you use the exact same angle. You take its cosine, you take its sine, you square those two numbers and add them together, you're always going to get 1. Even with like random angles that we don't necessarily know off the top of our head, you know, if we grabbed a calculator and we looked at what the cosine of 50 degrees was and what the sine of 50 degrees was, the cosine of 50 degrees, if we squared it, and the sine of 50 degrees squared, Those two things added together, always going to be 1. So this is the big guy to remember. Cosine squared, and you can, some people write it sine squared plus cosine squared. It doesn't matter the order because it's arithmetic, it's addition, and addition's commutative. So sine squared plus cosine squared or cosine squared plus sine squared equal to 1 is your first big identity. Okay. Before I look at the other two Pythagorean identities that are related to that, I'm going to come down here to the reciprocal identities. Because we already know these. Sine and cosecant are reciprocals. That means 1 over sine is equal to a cosecant, and 1 over cosecant is equal to a sine. We already knew that. So if we have a sine, we could replace it with 1 over cosecant. We hardly ever do that because that's not usually our favorite thing to do. But if we have a cosecant, we can replace it with a 1 over sine. My other two reciprocal partners are cosine and secant, and tangent and cotangent. When I do 1 over the cosine of something, that's the same as the secant. 1 over the secant is the same as the cosine. One over tangent, cotangent, cotangent, 1 over tangent. There's basically 11 identities that we have to remember. There's 3 versions of the Pythagorean identity. There's 6 reciprocal identities, and there's 2 quotient identities. So 11 identities total when we make our list. We already know 6 of them, or we should, or at least 6 of them aren't too bad. Most of them were like, okay, yeah, it's sine, cosecant. I remember talking about those are being reciprocals. 1 over sine can replace cosecant. 1 over cosecant can replace sine. 1 over cosine can replace secant. 1 over secant can replace cosine. 1 over tangent can replace cotangent. Oops, I wrote the same thing, didn't I? Didn't mean to do that. Sorry. 1 over tangent is cotangent, and 1 over cotangent is tangent. Yeah, I got it right. Different relationship. Okay. Today is going to be about taking expressions and replacing expressions in functions to replacing expressions in functions to get a simpler expression. Rewriting things. And so what we have to have available to us is our tools for rewriting. And our tools are going to be, what can I write something? What is another way to say that? Another way to say cosecant is to say 1 over sine. Another way to say cotangent is 1 over tangent. We will use these replacements to write expressions in different ways. Okay. All right. We still have 2 Pythagorean identities to talk about, but before we get to those, let's keep going into the quotient identities. These are two that I've talked about, or one that I've talked about, but I don't know that we've used it a lot. If you remember that tangent of an angle we talked about being equal to y over x. Well, y, if I wrote y as y over r, and I wrote x as x over r, that would still be the same relationship. I just changed those two numbers by dividing them by something common. And y over r is sine, and x over r is cosine. So the second most important identity after cosine squared plus sine squared equals 1 is that the tangent is equal to the sine over the cosine. I'm pretty sure we talked about that, and just like I may have mentioned it here and there when we were looking at ordered pairs on the unit circle, that was the quick way to get the tangent. You take the y over the x. And when we're talking about special unit pairs on the ordered pairs on the unit circle, that's a sine over a cosine. Okay. So the other one has to do with cotangent. If we use the fact that tangent and cotangent are reciprocals of each other, and that if tangent is sine over cosine, then cotangent, which we know we created was x over y, ends up being cosine over sine. Okay. I'm going to make a little list right up here. All right, so cosine squared plus sine squared equals 1. Sine 1 over cosecant. Usually when I write the reciprocal ones, I only write them going in one direction, but you can write them in both directions. If you want to write all sort of 6 of them. All right, so then cosecant 1 over sine, secant 1 over cosine, cotangent 1 over tangent. Okay. So that's the reciprocal ones. These are going to be the Pythagorean ones. Here's the quotient ones are tangent equals sine over cosine, and cotangent equals cosine over sine. That. We're almost done. We're almost done getting all of our different pieces that we need organized. Okay. We've got this whole chain of reciprocal, this whole list of reciprocal ones. We've got 2 quotients, and we're going to end up with 2 more Pythagorean ones. The reason I've kind of held off on the other 2 Pythagorean ones is because we're going to actually use information from the other identities to get the other 2 versions in the Pythagorean one. Okay. But that's a really good organizational list. Q for the quotient ones. You don't have to know what they're called, honestly. You just have to know their relationships. So you've got your quotient ones, your reciprocal ones, and then we're going to get 2 more on our Pythagorean list. I'll let you get those down if you need to, and then okay. All right. Now, I said early, if you learn the one Pythagorean identity, you can get the rest of them. So the main Pythagorean identity is that the cosine squared plus sine squared equals 1. If we took that statement and let's say I wanted to divide everybody in that statement by a cosine squared. Okay. So cosine squared divided by cosine squared, sine squared divided by cosine squared, 1 divided by cosine squared. This is going to make my second Pythagorean identity. A cosine squared over a cosine squared, that's a 1. But here's where we're going to need 2 other identities to finish this out. Sine over cosine is the same as tangent. So sine squared over cosine squared is a tangent squared. One over cosine. Well, 1 over just cosine is secant. That's the 5th one down on our reciprocal identities. A 1 over a cosine is the same as a secant. So 1 over cosine squared is equal to secant squared. And that is the second Pythagorean identity. If you take the first one and divide everybody by cosine, you get 1 plus tangent squared equals secant squared. So that's what I meant when I said if you know this one, you could make the other ones. The way you make this one from this one, divide everybody by cosine squared. Pythagorean identities have 1s in them. Yeah. The basic, the original one equals 1. The other 2 that we're going to write have a 1 inside them. So my third one, I'm going to start back with cosine squared plus sine squared equals 1. And this time, I'm going to divide everybody by sine squared. And that's going to make my third identity a cotangent squared plus a 1 is a cosecant squared. I'm going to write that on my big list. Cotangent squared plus 1, oops, I forgot my theta. Cotangent squared of theta plus 1 equals Now, the Pythagorean identities only work with squareds. There's no other version of them. The other identities, the quotients and the reciprocals, we can bring other powers in and they'll still work. Tangent is sine over cosine. Tangent squared is sine squared over cosine squared. We can change the powers and they work. Same thing for the reciprocals. We can change the powers and they still work. The Pythagorean identities only work for squares. So the versions of the Pythagorean identity, you can't have any other exponents on them. The functions have to be squared. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Those 11 things are what we're going to need to do 90% of the problems in this unit. So responsibility number 1 is to now memorize this chunk of information. Not too bad though. Like I said, the reciprocal, if you look at it like, oh my God, I gotta remember 11 weird things, then yeah, that's hard. But if you chunk them together, first of all, types of identities. There's 2 of this kind, there's 3 of this kind, there's 6 of this kind. Okay, that's easier. If you give yourself like, oh, well, I kind of already knew the reciprocal ones. If you know tangent and cotangent are reciprocals, then knowing tangent is sine over cosine, you can automatically get that the cotangent is cosine over sine. You can flip that. And then, like I said, with the Pythagoreans, if you can remember the first one, divide everybody by a cosine squared, and you get the second version. Start back at the original, divide everybody by a sine squared, and you get the third one. All right. That's a lot. And there's no nice, fun, pretty way to talk about these. You kind of just have to be like, these are some of the relationships. They're not all the relationships in trig. There are other relationships between different combinations of angles, but these are the ones we're going to start with. Because what we're going to do is we're going to take expressions. If we flip over to the next page, we're going to take expressions and we are going to rewrite them in a different way that's legal. Now, rewriting is kind of open-ended because you're like, well, how do I know I'm done? I mean, I can change anything. I could change everything in the problem. You know, what is my goal of changing it? Okay. Well, in trig, when we talk about simplifying, expressions that have multiple trig functions in them, we would like to be written with just one trig function if possible. Or, in some cases, we might not even have any trig at the end of the problem at all. The simplest form of a trig expression is you take out as much of the trig as you can. You either have everything in terms of one trig function. So instead of having like sines and secants and tangents all mixed together, we try to figure out a way to have like all of one kind of function. And if we can, it'd be awesome. We have no functions. We have no trig functions at all.